Let's take a look at some one-dimensional kinematics, and our goal for this is to develop equations of motion. That can be used to analyze scenarios in which an object undergoes a constant acceleration. Now you need to keep in mind that there are most situations in real life the acceleration is not constant. So for example, if you are in a car and you are accelerating in your car and the gears have to shift from, say, first gear into second gear, there's going to be a little hiccup as it does that, and your acceleration is not going to be constant. We're only going to be dealing with situations in this class where the acceleration is constant. A constant acceleration means that A equals a number. That's what we're talking about here. And we're going to start with, let's say that we have a car and we have, I don't know, maybe the fancy car that has the continuously variable transmission where the acceleration is pretty close to constant. So let's say that we have ourselves a car here. And it's going to go through a distance, s, and we can time it, so we can have our little stopwatch here, and it'll start at that time, and then it'll go to another time, and I need to make sure that I don't try to move the pen faster than the computer can handle it, and then once it's over here, it's over to another time, and we will call that time t. And we start over here at time t equals to 0. Well, the speed that it will have traveled at is the total distance that I'm calling s divided by the time. And very often we rewrite this as s equals vt. Often in math class, the math teacher will write it as d equals rt, where distance equals rate times time. Now in physics, we typically use s for displacement, d for distance, v for velocity, and velocity is the rate of motion. Now what if this car starts out at one speed and ends up at a different speed? What if the car starts out at 10 miles per hour and ends up going at 20 miles per hour? Well, since we've had a speed change here, probably what we could do, as long as this is a constant change in speed, we could average these two speeds together to get the average speed by adding them and then dividing by however many there are. So this would be 10 plus 20 divided by 2 gets us an average speed of 15 miles per hour, which we would then use to calculate how far did we drive in, I don't know, half an hour. Now let's take this average here, VO plus VF over 2, and we're going to substitute that in for this V here because this V is ignoring the fact that the velocity can change. So combining our average with this equation, we're going to get a new equation that we are going to record and use. And what we have is the distance is the average speed, but now we're explicitly saying the average speed is made up of an original speed and a final speed that we're going to add together and divide by 2. And then we multiply those speeds times time to get the distance. Notice how the fact that the car is accelerating is not actually in this equation. There is no A in that equation. So I call this equation the no A equation. Now in my other video where we did some graphical analysis, we also have the other kinematic equation of VO plus VF equals AT, where we found the slope of a velocity distant velocity time graph. And the slope of the velocity time graph is the acceleration, and then we could rearrange it into y equals mx plus b form, where VF is on the y-axis, VO is where the line crosses the y-axis, A is the slope, and then time is the horizontal variable. If you notice in this equation, there is no displacement listed as part of the equation. Between these two equations, we're going to come up with 3 more equations for a total of 5 equations for the 5 kinematic variables. If you take a look at these 2 equations, we have a VO in each equation, we have a VF in each equation, we have a T in each equation, but then we also have an A and an S. Those are our 5 kinematic variables: VO, VF, S, T, and A. V is velocity and O is original. Let's learn how to write here. That's better. Original velocity. And so far I've been using velocity and speed as interchangeable. They're not quite interchangeable, but they are related. VF is final velocity. S is displacement, or how far did I end up from where I started. It's the straight line. As I drew up here, it's the straight line. Even if the car actually follows kind of a wiggle, that wiggle would be a distance traveled, but from the beginning straight line to the end, the saying goes, as the crow flies, that's displacement, and that's usually what we care about in physics, is the straight line distance. Lowercase t is usually time, and A represents acceleration. Now, we use these letters because writing out the entire word every single time, if we're going to write the equation, takes a long time when we'll take up a lot of space on your paper, so we reduce it down to individual letters. What we're going to do next is combine these 2 equations in 3 different ways to get rid of one variable at a time. And so we are going to have a no VF equation, another equation for no VO, another equation for no T. And for each of those guys, we're going to get rid of the VF by substituting, and then we're going to get rid of VO by substituting, and then we're going to get rid of the T by substituting, and that will give us 5 different equations, one for each of the kinematic variables, so that in problem solving, the 2 primary skills that you will need to have are, in reading the problem, determine which variables on this list here for Vofista, if we're going to put them together in a single word, which of these variables were given to you in the story, and which ones are you asked to find, at which point you then choose the appropriate equation to find the unknown variable.